So welcome back again after the tea break. 11th lecture of the short course. Now we are looking at active vibration control. After tea break, before lunch, and after lunch then there is also the lab on active vibration control. Again, an introduction, or I skipped the outline, going directly to the learning objectives. First learning objective is that you can state the objectives of active vibration control. You are able to explain how local and spatially distributed destructive interference differ and which variants of vibration suppression are based on it. Then you can explain why segment-wise applied functional elements are particularly advantaged for modal vibration suppression, why we can't put just one large actuator on the structure and use it for vibration suppression. You're familiar with 4 different variants of active vibration control. We will have a look at 2 more in detail and 2 we visit just briefly. Then you can name challenges in collocated and non-collocated actuator arrangement for local vibration suppression. And you can also explain where optimal excitation points or positions for actuators are for modal vibration compensation. Active vibration suppression, for example, at the satellite reflector again, we have a perturbance, airborne noise, whatever, have a sensor detecting the signal of the perturbance directly or indirectly at some certain position on the structure. And then we use this noise to create a control signal for an actuator, which then calms down the structure or the vibration. Vibrations we have in many areas of engineering, and most of the time we don't want this vibrations, especially in rotating machinery, because they lead to material fatigue, impair precision. If we look at very high precision devices, such as wafer saws, for example, and they could also cause surface waviness and chatter marks in manufacturing processes when we use material removal machine tools. And the objective in general is the reduction or even the total suppression of these vibrations using methods of adaptronics or smart structures. So first we have a look at destructive interference. If we have an infinite, let's say, plate-like structure like this, and we have an excitation F on it, then the structure will vibrate in the mode, in a certain mode shape. We'll write this again. In a certain mode shape, for example, the first eigenmode, and it varies over time with the modal coordinate we had to look at in the last lecture. And if we then externally, or if we then use an actuator with an current voltage U to excite the structure in the same eigenmode, but with a 100-degree shift in phase, then both of these vibrations would cancel out, and we have a calm, not vibrating structure. So this is the idea of superposition of harmonic waves with the same wavelengths and the same amplitude, same vibration behavior in terms of space, but with 100-degree phase shift in terms of time. A short recap from the last lecture, even if it was only a few minutes ago. We had this equation where we can translate or project a spectral excitation at point K with these sum of fractions where the mode shapes, distinctive mode shapes I, in this case, at point K and at point L are in. And with this, we can get the deflection at point L with respect to the frequency again. And the sum of fractions here we called transfer function or transfer behavior of the beam, so transfer between point K and L. If we excite this structure here with the external excitation broadband spectrum again, then we can use this fraction HKL to calculate how the structure behaves at point L, how the vibration is there. And we see again that the vibration is filtered due to the eigenmodes of the structure. Filtered by the eigenmodes of the structure. Now we have two approaches to use destructive interference with our surface actuators. We can suppress a vibration locally. This would be this approach here. Or we could aim at a suppression by spatially distributed destructive interference of the standing waves. So this would be this approach, which would totally calm down the structure. Let's quickly go through the figures. So in the first row, we have an excitation here at point K. This is the Fs is the external excitation we want to suppress, and without any means of vibration control, we have at point I, now not W but U, the vibration of the structure. Similar to this, we have for if we look at a modal suppression, we would, for example, excite an eigenmode like the second eigenmode here with this excitation Fs again. Then in the second row, we have the effect of functional elements. So we placed surface actuators here at point L, which we would also use to induce a vibration in the structure by a control signal. And then the bending wave would also travel to the point I and would influence this point. Or we would, if we look at the modal suppression, we would excite an eigenmode like the external disturbance does now with the surface actuator. And here you can see again that the idea is to have the same, to excite the same eigenmode, which is excited, but with a 180 degree phase shift so that they cancel each other out. And now if we look at the third row here, then we use superposition again for the destructive interference. And if we look at the local destructive interference, then at point I, the waves meet, or we only look at the behavior or the superposition of the two traveling waves at point I. One is traveling from point K, where the excitation, the external excitation is to point I, and the other one comes from the actuator. And then the aim is that in this point I, this is the point we want to calm down. We have the destructive interference, so that this point is not vibrating anymore for example, in precision enhancement, when we only need a certain point to be calm or not vibrating, to have high precision for positioning robots, for example, then we could use this. And in the other case, if we look at the mode shapes, then we could use the actuator to totally calm down the structure. It would not vibrate anymore because we excite the same mode shapes as the external excitation, but within phase shift. Yeah. Yeah. So the aim is, of course, we need also a sensor. We will have a look at in a few slides, but the idea is that we look at this point with the transfer behavior and try to generate a signal, or I can use the pointer maybe, then it's also on the recording. We try to generate a signal and an actuation which leads to destructive interference with the external excitation only in this point. So we don't want to excite the yeah. So of course we also have vibrations here, but it would vibrate, so the structure would vibrate in any point, but except this point I, where we aim at to calm down the structure. Yeah. Yeah. Yeah, of course it is. So it's our look at this in this lecture is very general. So details like which actuator do we need, which control approach, and so on is not part of the lecture. Just to my aim is that you understand just the basic concepts. We have the local destructive interference, where you would look at one point and try to calm down this one point. And the other is the spatially distributed destructive interference, where you really use or try to excite the same mode shapes with a phase shift to calm the whole structure down.
The second case,
yeah.
Several places destructive interference will happen.
Mm-hmm.
Second case.
Yeah.
Here only locally.
Yeah.
Destructive interference.
Yeah. Yeah. So correct. So here we have destructive interference over the whole beam, and here we only have destructive interference here. So we now have a deeper look in the local destructive interference. We have a disturbance Fs at a location K. So this is the red disturbance here at point K. And this generates a disturbing vibration we want to get rid of. And we use the transfer function from point K to I to describe the vibration behavior of the beam at this point I. So this is this function 3 would describe this signal here, and we can counteract it by a counter vibration with an excitation acting at location L. So we would have an actuator here, which also has a function, or we can also describe this excitation with this function Fa, A now for actuator. And we need a different transfer function now from point L to point I. And with this we get also a description of the vibration at point I, but induced by the actuator and not by the external excitation. So this is described by equation 4. And then to suppress it, we state that the overall vibration at this point I should be the sum of the vibration induced by the actuator and the vibration induced by the external excitation or the disturbance, and this should be 0. And then we have here the behavior, so maybe we should write here W, not U, to have the figures in agreement with the equations. And then with the equation 5 from the slide before, we can transform it by this. So we have the fraction of the two transfer functions multiplied by the function describing the external excitation. And this would give us the needed excitation of the actuator to suppress the vibration in this point I. So we need two transfer functions, one from the location L to I, which is the disturbance path. So this no, it's the other way around, I think. So this is from K to I, the disturbance path. This is this one. And we have the counter control part from L to I. So it's a typo here. This should be K, and this should be L. And this transfer function of the counter control path could have minima, which would result in very large forces Fa. So independence of how this fraction look like, and if you have minima here, then you need then the outcome is very high forces for the actuation, even if the external excitation is not really large. So now we have a look at the second variance of active vibration control, the one we had on the right-hand side, the spatially distributed one, where we use the eigenmodes of the whole structure to suppress the vibrations. We can use this modal description of the vibration again we had in the last lecture. We have the generalized mass times the acceleration, we have the damping times the velocity, and we have the stiffness times the modal coordinate again. And then we have here again the external excitation, where F is the generalized excitation again, so the amount of excitation on the respective eigenmode we are looking at. And if the generalized excitation of disturbance and counteracting forces is identical, so if we can state that the generalized, so Fs equals Fa, then with this the associated natural vibrations can be suppressed. So yeah. Yeah. Yeah, it's a dependence, or it's a matter of definition of the signs, right? To have these. Yeah. Yeah. Opposite to have the phase shift. Yeah. But if you bring it over to this side, then you have the other sign. Maybe we can discuss afterwards. Okay. yeah, Fsi minus Fai should be 0, but yeah, it's let's say it's a matter of definition how the signs are defined. Yeah. So as we have introduced the basic concepts, the two we are looking deeper in, the local vibration suppression and the global vibration suppression, we are now looking at segment-wise applied functional elements, and we start with a functional element on the whole surface of the simply supported beam. Then we can again, without derive it in detail, come up with the general excitation of the beam due to the surface actuator. Coming in with the kappa B, I will look it up. And we have again the small signal behavior we already know, but we can have a look at different eigenmodes, and here we can see that if we put different values for I in it, so 1, 2, 3, and so on for the different eigenmodes, the first, the second, the third eigenmode, then only the odd eigenmodes can be excited, because the even ones are 0 again. Because in this case, if you have, for example, I equals 2, then we have, then this one gets 0, and then we have no general excitation at all. Because then we have here 1 minus 1 is 0, and then we have any excitation at all. So if we apply a surface actuator on the whole surface, we can't calm down the odd eigenmodes. We have no authority over all vibration forms. And if we look at the derivative of this general excitation, then without looking at it in detail, we can state that at locations of high curvature, the contribution to the work is particularly large. So if we have the second eigenmode in these positions of high curvature, we can do a lot of work to the eigenmodes or to the deformed structure. Now we are coming to really segment-wise applied functional elements. So we have two functional elements on the structure. And then we have a new description of the general excitation by these two functional elements. And here xne and xna are the start and end coordinates of the functional element. So for the first functional element, xna would equal 0.2L, and xne would equal 0.4L. Is it right? Yeah. And with this, we can have at least authority over the first two eigenmodes. If we look at this, we can, with a, let's say, positive sign of the voltage, we can control this eigenmode, and with a different sign, we can control the second eigenmode. However, the analytical solution is no longer exact, and we neglect the influence of the surface actuators itself on the vibration behavior of the structure. So for these two function elements or functional elements, we can write the general excitation for the first two eigenmodes. So we have two equations for the first two eigenmodes, in this kind of matrix form with a vector containing the electric field we apply to the or the generalized electric field we apply to the first and the second actuator, and then we can see if E1 equals E2, then we have no excitation of the second eigenmode, because then they would cancel each other out here. And if we change the sign, so if one has a positive and one a negative sign, and we put it in this vector, then the first eigenmode would cancel out. And with this, we can selectively control the first and the second eigenmode of the structure. And of course, this is a very simple example. If we have a more complex structure or want to have control over more eigenmodes, then we would need more surface actuators, and we have a longer vector here for the fields. So now coming back again to the local and global vibration suppression and to two other measures in terms of smart structures. We have 4 fundamental variants. 2 we already had a look at, the local vibration suppression, which locally suppresses vibration by temporal destructive interference, so only at one point the structure is calmed down. And we have the global vibration suppression, where we use the standing waves or the eigenmodes to attenuate destructive interference in the whole structure, at least for the eigenmodes we want to tackle. And the other 2 options, we will only have a look at one slide each, is active skyhook isolation, where we use we want to isolate vibrations by the use of an adaptive damper. And the other idea is to use electromechanical absorber networks, where we can adaptively set the cancellation frequency or change the vibration behavior of the system. I will show in a few slides. So coming back to local vibration suppression again, when we want to calm down more than one point, we can write this deflection at point, deflection u at several points as a vector, and have this transfer function HP as a matrix for primary path, and the primary path is from the disturbance to the positions we want to calm down the structure, and we can have the same equation 13, for the transfer function or the behavior from the actuation positions towards the points we want to calm down, and this is S for the index S for the secondary path. So the primary path is from the disturbance to the points we want to suppress the vibrations at, and the secondary path is our control path, where we want to quieten the structure. Now we can say again that the principle of destructive interference requires that these 2 vectors are equal, again a matter of sign, so that we have the sum to 0, that these points are calm or quietened, and this is satisfied when the transfer function of the secondary path times the vector of excitation equals excitation by the actuator equals the primary path times the excitation of the disturbance. And if the number of excitation points and the locations of vibration suppression are equal, then we can invert this matrix and calculate directly the vector of forces we need to calm down or to quieten the structure. So from this we can see if we want to do it with the inverted matrix and want to calm down, for example, 3 points in the structure, then we need at least 3 actuators to be able to invert the matrix. This is again a rather crowded slide, but we have a look at it together. So we can have 2 arrangements for local vibration suppression, the collocal or collocated actuator arrangement and the non-collocated actuator arrangement. We will have a look at this one here first. In this case, the actuator is placed at the position where where also this, the point is we want to calm down. So we have the point where this structure is disturbed or the external excitation is not the point we want to quieten, but the point we want to quieten is also the location where our actuator is placed. And if we then have a look at the transfer functions, the transfer function for the primary path is the same for both actuator arrangements, but the transfer function of the secondary path from the actuator to the location we want to suppress the vibrations at is different. And what is important, we saw, maybe I quickly go a few slides back. What is important is the inverted matrix of the secondary path times the matrix of the primary path, or here it is written down as the fraction of the 2 transfer functions. And we can see that due to this anti-resonance here, so we are in a node of the eigenmode of the vibration. We have a peak here in the fraction of the transfer functions, and this means that we need really high forces in this arrangement to calm down the structure at this point for this frequency near the second eigenfrequency. So we can directly read from this fraction of the transfer functions for which frequency we need high forces then to calm them down, the vibration. And therefore, usually the limit of the actuator, or the limited force the actuator can bring, is the limit for the vibration suppression in this collocal arrangement. Collocal or collocated means that the actuator is on the position where we want to calm down the structure. And non-collocal would be the second option we now have a look at. And in this case, we have the actuator not at the position we want to calm down the structure. So in this case, the actuator is mounted at a different location. And what now our limitation is the signal propagation time. We have different propagation times of the signal or of the vibration. We have the time theta p. This is the time the vibration needs to travel through the structure to this point we are looking at. And we have the time theta s of the secondary path. This is the time our counter vibration needs to travel through the structure from our actuator to the point, our desired point. So this is already a limitation that we need to place the actuator if the structure has the same cross-section overall then, or over the whole length, then we need to place this actuator closer to the point than our disturbance. And in addition, we have also some latencies, theta delta, which come from the filters and the digital signal processing, because what we need to do is we have a signal processing control loop. So our sensor is here to know the excitation force. And from this recorded signal of the disturbance, we need to calculate in the control loop our signal for the actuator. And this also takes time and also limits the positioning of the actuator.
Actuator has to preempt the disturbance.
Yeah.
Preempt the disturbance. So before disturbance comes, actuator has to.
Yes.
Create,
Yeah. That's correct. So we need the actuator to have the signal at this, or the vibration at this point at the same time like the disturbance would reach this point. But we also need some time to create the control signal for the actuator. And therefore, the actuator in general has to be closer to the position we are looking at than the disturbance. This is the limit if we have the non-collocated actuator arrangement. So in the first case, our limitation is that we need for some frequency really high forces due to the anti-net resonance. And in this arrangement, our limitation is the traveling time of the wave and the signal time, which limits the position of the actuator, or the in-plane position of the actuator. Now we look again at the global vibration suppression. So the modal vibration suppression, it's based on the destructive interference of the standing waves, like shown in the first slide of the lecture. If we can dominate the response, or the vibration is dominated by some eigenmodes, and we can suppress them, or have also the same eigenmodes excited with a phase shift, then we can really suppress the entire structure, or the vibrations at the entire structure at all locations, not just at one. And for this, we need, for the eigenmodes we want to control, that the modal coordinates are the same. And this we can achieve if the same work with negative sign is performed on the same mode shape. So the generalized force of the disturbance is the same like the general force from the actuator. And this can also be written as the vectors of the different mode shapes times the vector of forces for the actuator and also for the disturbance. So for complete systems in which the number of eigenmodes equal the number of degrees of freedom, we can calculate the vibration compensating forces by inverting the modal matrix here. In real applications, we don't have complete systems because we have indefinite degrees of freedom, and therefore the modal matrix is incomplete, and then we can help us out with a series expansion for calculating the vibration compensating forces. If we use a finite element model instead of a real structure, then we would have a finite number of degrees of freedom. Then we could also use this. And nevertheless, if we use this equation 21 or 22, we now have equations to calculate the needed actuator force in terms of the frequency from the disturbance using description of our eigenmodes. And there's another, let's say, slight change. If we use so-called modal force vectors, then the series expansion is particularly effective. What are modal force vectors? Modal force vectors are vectors of forces which only act on one eigenmode. So so the force distribution that performs only work on one specific eigenmode would be a modal force vector, and it would not perform any work on the other eigenmodes. So if we want to write this down, if we have a look at the eigenmode J, multiplied by the modal force vector I, then this would be unequal 0 if J equals I, so we can perform work on the same eigenmode, or it would be 0 if J is not equal to I, so all other eigenmodes would not be affected. Yep. It's called modal force vector. It's a force distribution, and it's specified as the force distribution which only performs work on one single eigenmode. Yeah. Sorry, come again.
Eigenmodes are already perfect.
Yeah. Yeah, yeah. So we have again the assumptions of our modal transformation. So we look at the modal description of the vibrations again. Yeah. Sorry? It's the force generated, so it's describing the force of the actuator. Yeah. Index A. Yeah. So everything with index A is with respect to the actuator, and S is the disturbance. Is from my German slides, because disturbance in German means Störung with a capital S. So therefore, it's FS. Yeah. I didn't change that.
So distance means what is in German, sir? Start with U?
Sorry?
Displacement starts with U?
No, but it's the common definition for, is U. So displacement would be Verschiebung in German. Verschiebung oder Weg, so the way. So force displacement plot would be ein Kraft-Weg-Diagramm. Kraft-Force, Weg, Displacement diagram. Yeah. And we can achieve this modal force vectors if we have actuators applied in segments, like we had a look at the comparison of one large actuator on the whole structure. With this, we can't control single eigenmodes or individual eigenmodes, but for our beam example, for the first two eigenmodes with the two actuators on it, we could control specifically the first and the second eigenmode, and this would then be comparable to the modal force vectors. And with this, we can also say that for the number of eigenmodes we want to suppress, we need the same number of actuators. So the number of eigenmodes we want to suppress determine the number of actuators we need for this global vibration suppression. If we want to suppress the first 3 eigenmodes, we need 3 actuators. Now, an open question still is which excitation points to use for the actuator. So where do we place them on the structure? And therefore, we can have a look at the optimal excitation points for the surface actuators. And this would be defined by the position where the maximum the maximum modal strain is occurring. So we can derive the eigenmodes with respect to the space. If we have a plate, so this is not for a beam, but for a plate-like structure, 2 dimensions, x and y, then where these derivatives are maximum, these are the optimal excitation points for the surface actuators. And for the bending vibration of plates, it would be the surface strain, which are determined by the modal strain times the or at first we have the displacement on the surface with this strain times the z coordinate, and if we then derive it another time with respect to space, then we get this surface strain for the bending. Sorry? It's for, the B is for bending vibration, so longitudinal vibrations L and bending B. So we look at, we have this simply supported beam, which has a bending line like this. We look at positions where the surface strain is maximum, because we can apply with our actuators in plane deformations to act on the structure. And with this, we can set up a criterion for the optimal placement, the so-called modal index, where we, for one mode shape, would sum up the actual strains of the structure where the sensors or the actuators are placed, and divided by the maximum we could achieve. So if we don't, or if these are same, if we place them really in the position where the highest surface strain occurs, then this modal index for the first eigenmode would be 1. If we cannot place them in the location where the highest surface strain occurs, then this one would be smaller than this one. This stays the same. Then the modal index is smaller. And this would be the description for one eigenmode. And if we want to have a look at several eigenmodes with several actuators, then we can simply use the product. Here we have in the denominator we have the maximum, the product of the maximum surface strains for the individual eigenmodes. So we use all eigenmodes we want to suppress here in this product. And here we have again, like here, the actual surface strain where we would place the actuators, because in real structures we are not able to place all actuators in the optimal positions. And to find a trade-off, the best trade-off between for the positioning for different eigenmodes, we can calculate these modal index. So even if the controllability is not optimal for each individual position, we can judge the trade-off with this. The third measure was vibration isolation, or the active skyhook isolation. We only have a brief look. If we have this single mass oscillator again, then we could have a passive damping with a passive damper, but it only works if there's a relative movement between the mass we want to calm down and, for example, the ground structure where a machine is built on. And if we are in resonance or close to resonance, it could be that also the surrounding structure starts vibrating. In this case, we don't have a relative movement here, and then this passive damping would not work well. And the idea is that we have an adaptive actuator, so not a passive one, but an actuator we could tune, and then we control it to not to the surrounding structure or the ground, but we assume that it's connected to the sky as an inertia which does not move, which is not physically possible, but we emulate this behavior by the adaptive damping system. Maybe, yeah, just as a brief introduction to this active skyhook isolation. So we have an effective damping near the resonance because we then still could emulate a relative movement between the structures. And the other thing is an adaptive absorber. Looking, for example, like this, we could have this adaptive absorbers at the interface points of the structure to the ground. And as you saw yesterday in the labs, we can change the stiffness of a beam using these actuators passively by open and close the circuit, but we could also change it actively by applying a voltage. And with this, we can tune this leaf spring with the mass at the end and use it as an adaptive absorber. This would be the last option we visit in this lecture. And from this paper too, I have these pictures from. They were able to show that at these maybe it was the second eigenfrequency, they could reduce the vibration or the acceleration by -5 decibels using these kind of adaptive absorbers. So second last topic in this slide is the structural dynamic identification. For the two variants of active vibration control, the local and the modal one, we need knowledge about the systems. So for the local destructive interference, when we only try to calm down individual points, we need the knowledge about the transfer behavior between for the primary and secondary paths. So we need the knowledge of the path between excitation and response. And for the distributed or modal destructive interference, we need a modal model of the structure. We need the generalized mass and stiffness. And we can identify it, of course, with modeling approaches, analytical or numerical modeling. Or we can do an experimental system identification by means of experimental modal analysis to build a modal model based on the modal parameters. For this, we have two options. Oh, so here is the setup. Maybe all of you are familiar with. We have the structure here with some acceleration sensors and excite the structure here, and then measure forces as well as accelerations. and use this measured data to have a non-parametric parametric or parametric identification. In a non-parametric case, we measure the excitation force at the location L, for example, and the response at location K. And with this, and we do this for different responses at multiple locations. And with this, we can define our frequency response in terms of the transfer function, which we need to calculate the forces for the actuators. And in case of the parametric identification, we really determine the modal parameters, so the eigenfrequencies, the eigenmodes, the modal mass, and the modal damping, and the modal stiffness, which is missing here. And this we can do in the time domain or in the frequency domain, and then transform it. So I've brought rather old, but I think good example. Good example. This is also at German Aerospace Center, but I think more than 20 years ago. So I didn't started doing research then. The idea was for this body in white to calm down the vibration in the car roof by having actuators and sensors applied to the car roof, and to actively suppress the roof panel vibration, which are excited by the engine harmonics. And to do so, first the modal analysis was performed of the body in white. Sorry. With this, the modal data were recorded, and the results of the modal analysis were then used to develop the adaptronic or system or the smart structure. And again, at first, the optimal actuator and sensor positions had to be determined using the modal index, and then also control concepts and were developed, and experimental tests were performed. I think here's a mistake in translation. And the results were that the second, third, fourth, 5, and 6 eigenmode were identified experimentally, and a first eigenmode could not be captured by the experimental measurement, but the second one at around 43 Hertz, the third one at 46 Hertz, the fourth at 52, and so on. And then the system was tested. We have here for sensor position 1 and 6, the amplitude over frequency. Sensor position 1 is here, this point. So actuator and sensor are placed next to each other. Here's position 1 and here's position 6. So for these two positions, the measurements were plotted, and this is the vibration response for the uncontrolled system. So system installed but uncontrolled. We can here see the second and third, fourth, fifth, sixth eigenmode again. So if we look here, it's between 40 and 45, maybe 42, 43 Hertz, which corresponds to this eigenmode. And with activated control, at least the eigenmodes from 2 to 6 could be calmed down or could be quieted. And the same here for sensor 6, where we have here the second eigenmode, here's the third, and so on, and it worked also on this sensor. So the modal vibration suppression should work with this kind of installation or setup. Okay, with this, I'm at the end of this lecture, closing with the summary. We have unwanted vibration in many areas of engineering. which impair the functions of technical systems. And we had a deeper look in 2 active vibration suppression methods. The local vibration suppression, where only individual points are suppressed at the structure. Then there is the modal vibration suppression, where the entire structure is calmed down, or at least the selected eigenmodes we want to tackle. And the takeaway is that the number of functional elements required for the modal vibration depends on the number of eigenmodes we want to suppress. So 2 actuators are needed to suppress 2 eigenmodes, and we have to find optimal excitation points, and therefore we can use the modal index, which relies on the modal strain of the different positions in the structure. And with this, I'm open for questions.
So is there any way
Yeah.
you can find the theoretically
Yeah.
what is the dominating mode which is causing maximum disturbance?
Mm-hmm. Yeah, I think it's
Model index.
it should be always the approach that you first have a look at the vibration behavior of the uncontrolled structure, and then see what eigenmodes are dominating this. In
In this case, maximum amplitude are getting at P4 like 64 something.
yes, here,
62.
and this corresponds 63. The 6th eigenmode seems to be the dominating one. Yeah, and I think in real structures, the influence of the higher eigenfrequencies decay, so maybe you have to look at the first 10 eigenmodes to completely or to nearly suppress all vibration. Yeah, I mean, you can perform finite element based modal analysis. If you have a model of your structure, you want to suppress the vibrations, and from the modal analysis you know the eigenfrequencies as well as the amplitudes, and then you can select the eigenmodes you want to suppress. So yeah, I think it depends as always how close the model is to the real structure, but
At least if you have model initially, then
Yeah.
experiments.
yeah, that should be possible. Yeah. 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 Mm. Yeah, you mean I think the transducer is bonded to the whole. So it's bonded. The surface of the actuator is bonded completely to the structure, and we assume what is Wirkungsgrad in English, Hendrik? Don't sleep away. No. We assume that I think all the vibration is transferred to the structure, but we may have some losses in reality. Yeah. Yeah, it would be a structural adhesive, for example, with. Mm-hmm. Mm-hmm. Yeah. 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 We can calculate it, but I think the goal is to have this interface so stiff that it does not influence the transfer of the vibration from the actuator to the structure. So you would not use some kind of very elastic adhesive, but a rather stiff one that you can transfer really the vibrations without changing the behavior.
Less damping is what chemical is that?
Sorry?
Less damping.
It's I'm not sure what if there's a direct translation in Germany. It's the Leersches Dämpfungsmaß. So it's how much these eigenmodes are damped by the structure without the control. Yeah. So how fast they decay if you excite them. Yeah. Okay, then Thank you very much. We are now at the